there. Okay, so this is what you will have access to for our Datum website. I'm sorry, our Datum classroom. So we will have a variety of classes, including Introduction to Energy Data Science with videos, exercises, lecture slides, subsurface machine learning, videos, workflows, Jupyter notebooks, all included, energy machine learning, pandas for Excel addicts. So you will have full access through our Jupyter Lab platform to all of this content. And simply, if you go to datum.io/access, this is what the the Google form looks like. Takes a few minutes to fill out, and you will be on our wait list whenever we are ready to launch that. So without further ado, I present Dr. John Foster today. Dr. Foster, the floor is all yours, my friend.
Thank you, Avi. Let's start by sharing my screen. So I think Avi mentioned that this would be everything that is possible with Python. Well, I don't think I can cover all of that in an hour. We'll show you a sample of things to do kind of within the context of data science and machine learning, with kind of a focus on things that petroleum engineers and or geoscientists might do. So I have a couple of just slides here just to kind of show you some overview things, not a lot of code here. And then I'll jump over and do some live coding to kind of give you a feel of what Python looks like in an environment that data scientists would typically use it in, and that is Jupyter notebooks. So first, a little bit about myself. In addition to being an instructor and co-founder at Datum, I'm a professor of petroleum engineering at the University of Texas at Austin. I'm also have appointments in aerospace engineering and engineering mechanics, as well as the Odin Institute for Computational Engineering and Sciences. And I advise students in all of those programs. My research is mainly focused on large scale computer modeling and simulation, and that includes both physics-based forward simulation, like you might think of reservoir simulation, for example. I, in fact, teach a class to undergraduates in reservoir simulation, and as well as data science and machine learning. But with respect to machine learning, I'm really interested in what we are now calling scientific machine learning, and that is incorporating the physics that we know into the machine learning model in some way. You can find me on, I have a lot of code on GitHub, a lot of stuff out there. You can find me on Twitter, elsewhere. And of course, you can always find me at the regular courses that we teach here at Datum. So let's dive right into the topic today. Now, I know the title of this class or webinar was, what can we do in Python? But typically when anyone says Python or talks about Python, particularly in the context of data science and machine learning, what they're really talking about is what we might call the Python data science ecosystem, right? So Python is a general purpose programming language, and just the core language in and of itself, while it's particularly useful for, say, system administration tasks and things like that, wouldn't be a terribly great language to do data science and machine learning, again, just using the core language. But when you wrap it or surround it with a lot of all open source third-party modules, then it becomes extremely powerful. So for example, NumPy is a module that gives us array data structures so that we can do numerical computations at close to the speed that C would give us, right? Pandas is what I typically refer to as kind of your drop-in Excel replacement, meaning that you can do all the types of tasks, data analysis tasks that you would typically do in Excel, but with the full power of Python behind it, and that you have a general purpose programming language behind it. SciPy is all of your numerical algorithms, so your root solvers, your integration routines, your interpolation routines, your ordinary differential equation solvers are all housed in this library. Scikit-learn is probably the world's most used machine learning framework. So it's an essential part of this toolkit. A couple of plotting libraries, Matplotlib, which is the de facto standard plotting library in Python, and great for making, publication quality plots. Basically, any visualization you've ever seen or any two-dimensional visualization you've ever seen can be recreated with Matplotlib. Bokeh is another plotting library that is more targeted for web-based interfaces and or streaming or large-scale data, big data. Panel is a dashboarding application. And then, of course, Git and GitHub are not really part of the Python ecosystem per se, but we interact with them a lot, as software engineers utilizing these tools. And all of these packages are packages that we cover in depth in our Intro to Energy Data Science class. So that class, to be kind of ready for that class, all you need is really some very preliminary Python syntax knowledge that you can typically pick up through one of the online training courses, free training courses like those offered at, say, Code Academy, for example. So you just need some very basic Python, and then we dive in on all these libraries and give you a feel for what they're about. Now, also, it might be intimidating to the uninitiated to say, well, wait a minute, Python happens to be on my Mac or Linux machine, but what about all those other libraries? How do I install them? How do I make sure they're compatible and whatnot? And so the answer to that is that the easiest way is to download the Anaconda Python distribution. So with that, it's a one-click download for Windows, Mac, or Linux machines, and you get a nice, sort of desktop manager for this ecosystem, in the sense that you can launch Jupyter notebooks and run Python. You can all these libraries are installed by default, all of the ones we discussed already. So there's nothing, other than installing the Anaconda distribution, there's nothing else to install. Again, we have no special relationship with Anaconda or anything like that. There are a couple other distributions out there, but for the most part, we recommend Anaconda, and I think that it is the most popular Python R data science platform out there. So I think you won't be alone if you choose to use Anaconda. But this is how you get Python and all of the packages that we will discuss today and in our course onto your computer. And again, it's completely free. All these packages are open source. So let's just look at kind of a very generic thing you can do with Python. And this is all just using the core language. So again, it is a general programming language. So for example, you can do things, write for loops and conditional statements. And in this case, write a function. So the keyword in Python to define a function is def. This function takes two arguments, nx and ny. Nx and ny are intended in this example to represent the number of grids in the x and the y direction. This example is actually pulled from reservoir simulation and builds a pentadiagonal matrix that we could use to develop a reservoir simulator, at least for single phase flow. So the matrix that's created is here and has a special structure. Along the diagonal, the numbers refer to the number of neighbors for any grid block. So each row in this matrix refers to a grid block. So for example, 0, it has two neighbors, 1 and 4. So in the diagonal entry, you'll see a 2, and in the 1 column and in the 4 column, you'll see a -1. Those correspond to the grid block numbers of the indices. So it has a special structure, and there's nothing particularly interesting about this. So just to show a fairly complex example of writing a function that takes two arguments and produces this matrix with a for loop and some if statements, as well as some built-in functions like sum and absolute value there. So this is kind of just an example to kind of show the Python in the raw language, if you will. We can also use a package, I mentioned earlier, pandas. Pandas is, again, just what I consider to be kind of a drop-in Excel replacement. It's far more powerful than Excel, and we'll see a couple of examples later. I have a couple of examples when I'll be live coding and showing you uses of pandas. But for our purposes here, what we'll see is just if you have what's called a data frame, and it very much looks like an Excel worksheet, except across the top, instead of just seeing alphabetical numbers, you have actual labels, and you can refer to the columns via their labels. So the labels have a little more meaning or add readability to your code, as well as an index, which is essentially just a row label. In Excel, of course, the row label is always just a monotonically increasing set of numbers. But here we can actually set the index to other meaningful things, like, for example, dates or time steps if you have time series data. And that allows for some ease in plotting and other things. So there's some petrophysical data, an example of it. I'm only showing there's actually 200 samples in this data set. I'm only showing the first 5 rows here. But you can see that basically every value that has a porosity greater than 0.12 is labeled high, and every value of porosity that is labeled that has a value of porosity less than 0.12 is labeled low. And so we can create like an Excel pivot table that will aggregate the high and low values, and then have the aggregation function set to median. So with that, this is what I'm not hiding the code here. I'm hiding the code here again, because again, this is just kind of a highlighter overview webinar. But basically with just one line of code, I can perform this kind of aggregation, which to create this pivot table, which would be a common thing you would do in Excel, for example. Of course, plotting and curve fitting. So in this case, we have some time series data that actually plots so the blue line is some actual production history data for a well. And in this case, we've fit an ARPS decline curve to it. And in the live coding example that I'll be showing later, I'll actually work through a very similar example to this. So we'll go more into detail there. But again, with Matplotlib, this was created with Matplotlib. And as I mentioned earlier, essentially any two-dimensional visualization you've ever seen, pie charts, bar charts, line and scatter charts, anything like that can be recreated with Matplotlib. Also some contour plots, surface plots, as well as some rudimentary 3D plotting as well. But they're for 3D plotting, there are possibly better libraries out there. We can make interactive dashboards. So again, this is a Matplotlib plot, but now I have some interactivity or some widgets here that allow me to manipulate the plot. So if I go here and select the API number and change it, you'll notice that it takes a second, but the plot updates, right? So the API number changed, also the time series data changed. This is made with the library called Panel. Again, all we do is write Python code, and we get these interactive JavaScript widgets that are can be displayed in a web browser, can be deployed to the web. And what I'm, of course, again, I'm hiding the code here, but in addition to that, what you don't see is that these are actually making live calls into a SQL database. So that's why it takes a moment to update, because every time I change the API number, it's actually going out. You can see this goes into 2020 here. This is not stored data. This is actually a live call into a database, which pulls over the gas production history in this case for that well, corresponding to that API number, and plots it to the screen as you see here. So this is another example of a highly interactive visualization. This is using the library Bokeh, which is really built for targeting web applications. Let's see, it looks like I have a question. So I had a question, what is an API number? So yeah, I guess I'm making the assumption that the audience is a little bit familiar with, this is an oil and gas audience, because that's our target customers here at Datum. And so an API number is just a unique number that's assigned to every oil and gas well in the world, right? So, given that number, there's a lot of other information associated with that number, but when any well is given a permit to drill, it is issued an API number. So it's a unique number that corresponds to every oil and gas well in the world. So Bokeh allows us to create these kind of web targeted type visualizations, and you'll see that this is highly interactive. So the first thing that you'll see is that the wells. So these are wells that the operator EOG owns in the state of North Dakota. So these are all of EOG's wells in North Dakota here, and they're colored by cumulative oil production. So just at a glance, without doing much else, you can see that here in this region, where my mouse is, close to just to the right of my mouse, it's kind of a hot spot of the reservoir for EOG's wells. These are the highest producing wells. Also, there's tooltips on these wells. I can, for example, zoom in to a region. I can hover my mouse over any given well. It shows me the API number, and it shows me the cumulative oil and gas that has been produced from that well. So, and that's the case for all of these. Also, you'll notice as I hover over the wells, the plots at the bottom change. So that actually brings up the production history for those wells. In addition, I can select a number of wells and have those production histories frozen down here. So if I go down here, then I can expect this is the oil production for that API number. This is the gas production for that API number. And so I can go in and inspect those different wells. And you can see this is very fast, right? I mean, this is, again, every well that EOG owns, and I can rapidly inspect them, and you can see it update in real time quite rapidly. And again, I can go in, I can say zoom in on a region, I can select an individual well, and then it's frozen. I can come down here and inspect it, and then I can, to unfreeze it, all I have to do is just click on the blank canvas, and then I'm back to the interactive. So again, all of this was written in Python using the library Bokeh. So let's see, where do you find your dates linked to that data, and how is it updated so far? So this is public data. We have our, here at Datum, we have our own database that is kind of equivalent to what if you're used to Drilling Info or IHS Market's database of the, or aggregation of public data. So all the states that have commissions that govern the production of oil and gas will have some publicly available data. And in this case, we have aggregated the publicly available data for all of those wells and put that into a database that we can access. So the dates and other things that are linked to that data are just what are published in these public databases. Okay. So by the way, keep the questions coming. Happy to answer any questions that might come in. So I think with that, this is just kind of an overview, a couple of whiz-bang examples here of things you can do in Python, but let's go in and see how we might actually write some code in Python and go through a couple of examples here. So to do that, I'm going to go over to our classroom. Again, if you register for one of our courses, or as Avi mentioned earlier, if you fill out the Google form, we're getting ready. So if you take one of our courses, you'll be given access to this immediately. We're getting ready to scale this up to where thousands of users at any one time can be using this, not just limited to the tens or hundreds that may be sitting in our class at any given time. So when that rolls out, we'll be offering access, if you fill out that Google form, to everyone. And again, there's a couple of courses that we teach, like Introduction to Energy Data Science, and all the available lectures and exercises and associated videos. Same thing for subsurface machine learning. We teach an executive overview course, Introduction to Energy Machine Learning. I teach a 2-day course that kind of goes deep dive into pandas using and comparing to or developing workflows that you might be used to doing in Excel. So if you take register for any of our classes, you'll be given access to this. But from here, what I'm going to do is I'm just going to open up a new Jupyter notebook. So the Jupyter notebook, if you're not familiar, I'm going to tell you what it is. Again, this is not necessarily associated with Python, but is what everyone kind of considers part of the Python ecosystem, Python data science ecosystem. You can code in other languages in these Jupyter notebooks as well, like R. I think there's support for I don't know, close to 50 different languages now. But we'll be coding in Python. And so what you have in a Jupyter notebook are a set of cells, principally. And what we're going to do is we're going to write code into those cells and then execute the cell. So for example, in the simplest case, I can just write, just do some arithmetic operation like 2 + 2. And the way I execute a cell in a Jupyter notebook is I just type a shift enter. So that'll execute a cell. And then, I can do other things like, for example, I could write a function in Python. Like if I wanted to add two numbers together, what I'll do is define a function called myAdd, and I'll just simply return the two numbers. And then I can call the function with two arguments like so. Again, each time, I'm typing shift enter to register the function, and then again, shift enter to call the function. Now, what makes Jupyter notebooks really nice is the ability to intermingle rich text, code, and outputs of plots, as we'll see later. So as an example of how to intermingle some rich text with our code, what we'll do is I'll take, if you notice, I'm highlighted a code cell here. What I'll do is go up here and I'll switch this from code to something called Markdown. So Markdown is a lightweight markup language. So most people are familiar with HTML. HTML is the markup language behind web pages. So Markdown is like that in the sense that you provide a little bit of an additional syntax as you're typing sentences to provide rich text, hyperlinks, other things like that. So for example, now that I've switched to Markdown, what I can do is type a sentence. For example, this is Markdown. And if I surround the word Markdown with asterisks, I get bold text, and you get some syntax highlighting there. But if I type shift enter, what you'll see is that this is actually rendered as rich text, and I can go on and continue this. So this is a link to datum. For example, and now I have a hyperlink here that I could open in a new window. I might have to put the there it goes. So now we have a hyperlink there. Returning to our Jupyter notebook. You can do other types of syntax highlighting. For example, that's italics. You can have quotes. You can have raw code cells. So I'm just going to give it a hint as to what kind of code I'm going to write so that the syntax highlighting will be provided. But here then I can say, I'll just write the same code as above. And there I have code cell. Now this is not active code. This is just code that is written in the text, but is highlighted like code, for example. And then the final thing I'll point out with respect to Markdown is that you get really nice, and this is probably for engineers and scientists, this is very important. And when we document our code and workflows, that we can write equations, in a way that looks mathematically, correct. So I'll to write an equation, I'll use dollar signs to surround the equation, and then I will type some syntax that is called LaTeX. If you're familiar with it, it's a typesetting language, LaTeX. That's LaTeX. That's the syntax I'm using here. Must have an unbalanced set of parentheses somewhere. There we go. So yeah, I have an equation that's that is a function of t that takes parameters q, b, d, and t and produces a curve. And this is the well-known, this equation, in fact, is the well-known ARPS equation that is used for decline curve analysis, and we'll be using that here shortly. So I have a question here. So there's a question: if you read data from a file, do you need to validate data, perform data cleansing? What are the usual tasks are done when data files are read with Python? Yeah, so the recommended way to that I typically recommend for kind of small to medium sized files. When I say medium, I'm including files that could be up to a few gigabytes in size, several million lines of code, several million rows of data. The recommended way that I would recommend to read that in would be using the toolbox called Pandas. Pandas has some great functionality for parsing, particularly CSV files, comma separated value files, but also other types of generic data files. Gives you a lot of options as to how the data should be parsed, how dates are handled, other things like that. Again, we cover that in detail in our energy data science class, as well as kind of really deep dive into pandas in our Pandas for Excel addicts class. There was a question earlier that said, is the Python script for this visualization available on GitHub? It is actually on GitHub. I'll have to perhaps, if you want to follow up with Avi, send an email to Avi or and I can show you where that is. So another question was how to choose when to use Jupyter and when to use Spider. So Spider is a integrated development environment that if you've ever used MATLAB, it's very similar to MATLAB. It almost looks like MATLAB. I think that's just completely a matter of perfect personal preference. I typically use Jupyter notebooks for visualizing and reporting data more than actually writing code. So, I could use Spider or simply just write a script, using some other editor like VS Code, and then basically just import the script, and that's where in the script would be where all the kind of sophisticated code would be, and then just perform the visualization and reporting, the output of that code in a Jupyter notebook. And part of the reason for that is that kind of leads into another point. Is part of the reason for that is that you can actually export Jupyter notebooks in a number of different formats. So for example, I can go here. Let me save this, what I've written, go here and say export notebook as, and you're given a variety of options. So for example, probably the easiest thing, maybe I can export notebook as a PDF. I will download the PDF to my computer. It just opened here on my computer. So let me share that with you. Just show you what that looks like. So this is the PDF that was produced, which contains all of the data, including the hyperlinks, the equations, everything like that. But now I can just, of course, attach this to an email or something like that. So that's another nice thing about Jupyter notebooks is they're great for producing these kind of quick reports. So returning to our code example. Okay, so what we're going to do next is we're going to actually use this decline curve here to, we'll use this equation to fit a decline curve to some data. So the first thing we're going to do is we're going to get our data. We're going to pull it from our database here. So what all I have to do is give an API number. and then I'll print the output of that to the screen. And so here you can see what, basically this is provides a database call for us, which brings out the production history for the oil, the gas, and the water, as well as a date timestamp for this particular API. So I think what I'll do just to quickly show you what this data looks like. And these are pandas commands I'm writing right now. So this is the output of this is called a pandas data frame. And pandas data frames have certain built-in functions that you can call on them, like for example, plot. So in this case, it's plotting the oil and the water. There was no gas for this well, versus the timestamp here. And one thing I noticed immediately is that there's some missing data here, right? So this is very common when, it's a common thing when we have data that there's some missing data. And so we need to do something with that missing data in order to be able to fit the time series to this, because in fact, the fact that it's not plotted right there is because there's actually was a so-called NAN. There. So let me see if I can pull it up, which column it's in, but volume, oil. So there's at least one, let's see. Yeah, there it is. So yeah, the 12th month, for whatever reason, you see there's a NaN or not a number there for whatever reason. I actually don't know exactly why that is, if it just wasn't reported for that month or whatever. But when we go to fit a decline curve to this, the code will complain about the not a number. So what we want to do is actually replace that missing value. And I think this is a good example, because a lot of our data has missing data. And what we're going to replace it with, there's of course a lot of options, but in this case, I think the most obvious thing to do is just to replace it with an interpolation between the other two, right? So we're just going to choose a point that's interpolated between the 2 points that surround it. And we can do that using built-in pandas commands. So again, we're going to pull off the oil column. That's the oil data there. And then we can call this function interpolate. And the method we'll use is polynomial of order 1. That's a linear, right? Just a straight line. And so now if we were to say, look at the 12th line of what is we know that the 12th row was the one that was missing before. So if we take the 12th row now, you can see that there is a value there. It's no longer NaN. I think it should actually be that one. Yeah. So there's a value there now. It's no longer a NaN like it was before. I think just to maybe look at spread of, see how it was interpolated, we can do this. So that the 11th value there, which corresponds to the 12th row, was interpolated between the other two. Okay, so now we've fixed that issue. We can move on. And what I'm going to do now is, in fact, just assign this to a variable that I'll call oil. And I want to strip off just the raw data. So if I just type to NumPy, that gives me a raw data array. So if we look at what that is, it's just the raw data that's in that. It's no longer in this data frame type format. In addition to that, we'll also need the X data, which is the months, which happen to be just happen to be those. Yeah, so the question came in and says, what's an efficient way to explore a library and know their utilities? Thanks in advance for answering. Great presentation so far. Well, thank you for the last comment. Well, the best way is probably to take our energy data science class. I mean, that class is really meant to be an overall survey of all these tools and the capability of the kind of core libraries that make up the Python data science ecosystem. In the absence of that, though, essentially, if you were to go and look at the documentation, the API documentation for all of these tools, they're really well documented, and they also follow a similar documentation format. So once you get used to looking at the documentation for, say, NumPy, it'll be real easy to read it for Pandas, for Matplotlib. They all use a similar documentation tool set, so they all kind of have a uniform formatting, which makes it easy to read once you get used to it. We even talk about that aspect of it in the energy data science class. Other than that, it's a pretty open-ended question. There's so many utilities, and it's difficult to kind of, I think a class like ours, or there's probably some other ones out there that kind of offer these overview surveys, is probably one of the best ways to get into it. So, okay, so I have, oil essentially, which is my Y data, if you will, and months, which is my X data, if you will. And from that, then I can fit a curve. Well, the first thing I have to do is define a function for that curve. So, remember this is the function that we're going to code up. And in fact, I'll just open a cell here and write it here so that you can see it. So I'm going to define a function. I'll just call the function arps. The first argument will be t for time, and the other arguments will be the qi, d, and b. And then that's just going to return qi. So now I'm actually writing Python code for that function. And so now I've defined that function. We'll use it below in fitting the parameters to this model. So what we'll do is we'll say, we're going to store the output values in the variable parameters. We're going to use SciPy. This is a library, SciPy, optimize, curve fit. And well, the first argument to that is the function. I guess another answer to your question earlier that relates to Jupyter Notebooks that I might have not mentioned before is that if you happen to know what the function name is, for example, in this case, SciPy optimize curve fit, but maybe you don't know the arguments of the function or the structure of the function or exactly what it does, you can actually get that right from the Jupyter Notebook. If you put your cursor and you type Shift Tab. So if you put your cursor on the curve fit and you type Shift Tab, it will automatically bring up the documentation, right? So the documentation is, this is a nonlinear least squares to fit a function f to data. And the formatting is f, that's the function you want to fit, the x data, the y data. And then if you go down further, it also tells you that the function should take the independent variables, the first argument, and the parameters you want to fit as additional arguments, okay? So we did that already when we defined arps. But anyway, that's another way to get the documentation. I guess, yeah, I think I'll just leave it at that. Okay, so the function we want to fit is arps. The x data is months. The y data is oil. And what we can also do is, this allows for additional arguments like one called bounds, which allows us to set the bounds or do constrained optimization for our parameters. So let me type this in and then I'll talk about what it is. So these are the lower bounds of our parameters. So our three parameters are the QI, the D, and the B, okay? So given those three parameters, the lower bound for all of them will be 0. The upper bound for QI and D will be infinity, right? So they can be as large as they want to be or they need to be. but we know that the B value only ranges between 0 and 1. So we'll go ahead and put that information in so that we have, we're doing some constrained optimization. So with that, if we run this, there we go. Those are the parameters, right? So the value of QI is 1800, 0.07 for D and 1 for B. And so now that we have that, we can go ahead and plot it if we want. One way to do that would be to create another data frame. Probably the quickest way would be to create another data frame. So in this case, the month and the oil columns of the data frame are going to be what they were, but now we'll have a new column called model, which will be the ARPS model evaluated over the months of production with replacing the parameters like so. And then we can set the index to month. Let's see, months, I had a typo there. And then we can actually plot this. So there we have, our production data, of course, with the missing value replaced, and now we have a decline curve fit to it. Of course, we can use this decline curve to, for example, predict EUR, whatever, do our well economics. We cover a lot of that, a well economics workflow in the Pandas for Excel Lattice class. So the last thing I'll do is just show you how you can also do some additional things or add some interactivity to this. So if you've ever done decline curve analysis, you'll immediately recognize, I kind of purposely chose a data set that had a fairly nice decline that the ARPS model fits well. That's not always the case, and sometimes it takes some kind of manual tweaking to get a good fit to the data. And we can actually create a pretty clever tool to do that right within the Jupyter Notebook. So what I'm going to do is I'm going to just define a function that I'm going to call adjust Q. And what I'm going to do, what that will allow me to do is just perturb Q by some value, right? So initially I'll just set the default value to 0. And then I'm going to go back up here and I'm just going to copy these 2 lines of code and paste them into my function. Except now what I'm going to do is when I replace the parameters here, in addition to that, I'm just going to add a perturbation to Q. So Q was the first Q was the first of those parameters, right? It was Q, D, B. We won't mess with D and B for this purpose. Of course you could, but in this case, we're just going to perturb Q like that. Now I can call this function, like for example, I can call adjust Q, and for the value of Q perturb, I can set it to say 2000, which would add 2000 to the value of Q. And you can see that it's a little bit different, right? My curve has moved a little bit, right? And so you could go on doing this if you want. You could add 10,000, and you could go on adjusting it till you get a better fit. But the nice thing about, this kind of Python ecosystem in these Jupyter notebooks is that I can use a really simple feature called interact that will allow me to basically create on the fly here an interactive dashboard or widget. In this case, I'm going to set the range of my perturbation to be from minus 10,000 to 10,000 in steps of 100. And if I just do that, I'll go ahead and delete this line here. So the only thing I did from the original function was I added this one line of code. And now all of a sudden I have this interactive widget that will allow me to, interactively and sort of on the fly using the visualization, adjust this, right? Now say you did this manual adjustment, then you wanted to know the output parameters, right? Well, I could do something like add an additional variable argument called print params, and then I'll just say if print params is true, then print this. And so now this allows me to adjust it. And then, for example, if I wanted to see what the values are after it was adjusted properly, then I could just click this print params, and then there's the 3 parameters. Of course, I'm making no effort to style this in any way and make it pretty, but that's all completely available within this framework. So it looked like there were a couple of more questions that came in. So so any cases where scripting IDEs like Sublime would be recommended over Jupyter Notebooks? Yes, of course. I mean, I mentioned that earlier, right? I didn't mention Sublime by name, but it's an editor. I mentioned VS Code. I do most of my Python development in Vim, the old school Unix editor, just because I'm used to it and productive with it. So yeah, I mean, I would say that there's a lot of advantages to using, integrated development environments for, writing your Python code, and then just using a Jupyter Notebook to basically import and run the functions that produce visualizations. And then, of course, writing rich text to explain those visualizations. So, I think a lot of people start off in Jupyter Notebooks. They're great teaching tools. They're great learning tools because you can see how, every line of code is executed in isolation in a Jupyter Notebook. But once you get more advanced and you want to add some speed or productivity to your development, then using an integrated development environment or like or an IDE like Spider, like PyCharm, Sublime Text, Vim, VS Code, any of those things would be advantageous.
John, I actually haven't tried this before, but I know the extension for Python notebooks is .ipynb. Are you able to open those in other IDEs, or do you have to open those within Jupyter?
Yeah, you can, when you install the Python plugin for VS Code, you can open them in VS Code. You can open them in PyCharm. I use a plugin in my Vim script called JupyText, which converts the IPython notebook to essentially markdown and code on the fly, and so you can do it that way. It's a pretty nice, quick way to edit Jupyter notebooks from Vim. So there were a couple of more questions. When I make the request to connect to datum.io, you get a 403. My GitHub username. Well, you have to have been given permission to get to the classroom. So that's likely the issue there. When you do visualizations, how do you treat null values? I think covered that, right? Why do we interpolate for NaN value than taking the mean of all the columns? Well, in this case, it wouldn't make sense to take the mean. The columns represent different things. So one column was oil, one column is water. So it wouldn't make sense necessarily. They're also time series data, right? So if it was porosity, to take the mean or the median of a sample of porosity might make sense. But in this case, interpolating between the two, where you have a time series in which the production is declining, right? The purpose of this course is not to basically instruct you, or the purpose of this webinar is not to instruct you on the proper way to do data imputation. I was just showing one example for this problem that I think makes the most sense for time series data. A couple of more questions about, again, just, you have to be explicitly given access to our classroom. And that's why you're seeing those errors. And there's a link there for our 5-day intro to energy data science class that Avi posted. That's all I have for today. I'm happy to stick around for a few more minutes and answer any more questions if they come in. Thank you. Any sources, open source material to develop a grasp on machine learning for oil and gas? Well, again, this is kind of the purpose of our business. We didn't feel like there was any great kind of aggregation of this kind of information out there, and that's what we're trying to do here at Datum. So we teach a course on subsurface machine learning. My colleague that teaches that class, Dr. Michael Perch, has a lot of online information, YouTube videos and other things where you can access some of the kind of lecture material that would be very similar to what we cover in our courses, but our courses also have a lot of fully developed and documented workflows that are advantageous. There was another question: is there a reason to use R? It's just a matter of preference. If you learned R in school, particularly if you're a statistician, you might have learned R. R is very powerful for data science and machine learning. I would argue that Python is a better sort of general purpose programming language. In other words, there's not a lot of system administrators out there that use R to do system admin tasks. While you possibly could, there are many that use Python. And the reason for mentioning that is that means that, the more users that are out there, the more help you can, the easier it is to find help. Python is one of the most popular programming languages in general in the world. I think in the latest poll or index, only Java is more popular, and Python has been rising up those rankings over the last few years, and I assume it will be #1 at some point, which means the community is very large. And if the community is large, you can find help for the problems that you might have, Stack Overflow and other things like that. A lot of questions coming in now. Not sure I understand the question about non-unique combinations of answers for this particular problem. Does it work in variogram analysis? 360 rotation for data analytics for major and minor. Yes, that you could do anything like that. We actually cover variograms in our subsurface machine learning class. Is Jupyter used for professional purposes too? Not sure what you mean by that. I regularly use it for reporting, for hosting documentation of code on the web. I think that's all, professional purposes. Couple of more comments coming in. I don't see any more questions. So I think, Avi, I guess we can probably go ahead and end this.
Cool. Thanks, John. Great lecture. Appreciate it. Yeah. The recording will be posted as well. So for anybody that wants to refer back to it, I'll be posting that on YouTube. So thanks a lot, John. Appreciate it.
Thank you, everybody.